Hello, Advanced Geometry. Today we're going to do more calculations with circles. So first of all, a sector is pictured here, this shaded region. Officially, that is the region bounded by, you have two radii, right here and right here, and an arc, which is that arc AB. So that region is called a sector. We sometimes just think of it as a piece of pizza. But it is part of a portion of the area of the whole circle. The arc length is part of the circumference. So if we were talking about arc AB, that would be it's linear, a linear distance, even though it's curved, the linear distance basically from A to B along the arc. And as I said, that is part of, or a portion of, the circumference. Sometimes we can say it's a fraction of the circumference. So the formulas to actually calculate those things do come from things you know. So we have a circumference formula that'll give us the entire linear distance around the circle. Well, we only want this piece of it. So we have to calculate a fraction that will go along with that arc AB. And we can do that using our either arc measure or the central angle. It's generally easier. So I'm just going to put a letter here. So just use an A. Let's say that's A degrees. Now, as we know, that's the same degrees as the arc measure. Well, all the way around the circle, or the total of all of our central angles, always add up to 360. This is just one portion of that 360. So we're going to start by saying, all right, so we have a fraction equal to that central angle over 360. That is this angle, and that is a fraction of the whole circle. Okay, and then we're doing a fraction of, for the length of the arc, of the circumference. And as we know, the circumference is pi times diameter. Okay, or 2 pi r. You can say it either way. So it'd be this part of the whole circumference is the length of that arc AB. You can use similar logic here. So for finding the area of the sector, this central angle tells us what portion of the circle this sector represents. So again, we're still going to use that same fraction. This is the portion of the circle, but this time we're doing an area. So it's the part of the whole circle area, which we know is pi r squared. Okay, so this is the part, and then of is times, and then area of the circle. This is the part, and then of is the times, and we're going to do the circumference. Okay, so there's our formulas we're going to use. Couple of more vocabulary words. So annulus, so the region bounded by two concentric circles, so circles that have the same center. We can sometimes call it just donut, but the official word there is annulus, so the shaded region outside here. Okay, an annulus area. I like to sometimes do this with words first, but if you think about it, if we do the big circle area, so I find the area of this entire big circle, and then I take away that white circle, so the small circle. That should leave me with the shaded region. So big circle area, obviously with the capital R, is going to be pi r squared. And then the small circle area with the lowercase r is pi r squared. So that leaves us with our formula for the area of an annulus. Next, a segment. So the segment here is shaded, and that's the region bounded by a chord. So chord ACD. and the intercepted arc. So the area between this chord and its arc, that little spot there, is a segment. Again, I like to write this as words to start with. So if you can imagine, we have this sector here, that piece of pizza, and if we find that area, and then we take away the white triangle, that will again leave us with the shaded region. So you got to think sector minus triangle when you're doing the area of a segment. Well, as we know, I don't really actually ever write out the formula for this because it does depend on the situation as far as what you are going to use to find the area of that triangle. So just remember it as sector minus triangle, and however you can find those areas, you're going to use that. Okay, so we're going to try just these first two examples, and then I will go through them. So pause and try these first two. Okay, welcome back. So we're doing a length of arc AB. So we have a central angle of 72. So looking at our formula, we know right away we're going to do 72 out of 360 is the fraction. And we're going to do that for the circumference. So it's a fraction of the circumference. Okay, so pi times, we have a radius of 5. That is a diameter of 10. So I have 72 over 360 times pi times diameter. All right, so we're going to try to do this stuff without using calculators. Okay, we really need to get good at fractions. We need to get good at reducing fractions, multiplying fractions, all that business. So we're going to practice that a little bit here. So 72 out of 360, you will get good at recognizing what goes into 360. But I'll just kind of go through a reducing process, and then eventually you'll just recognize what those fractions are. But I see a 12 that will divide into both of these. So divided by 12 is 6. Divided by 12 here is 30. And then 6 obviously goes into 30, so this turns out to be a 1/5. Okay, so I'm doing 1/5, and then generally we write it as 10 pi, like that. So there's a couple of ways you can go about doing this. You can recognize 1/5 of 10 as just 2, or you can write this as 2 fractions, putting that over 1, and then this becomes 1 times 10 pi, and then on the bottom denominator is 5 times 1. But either way you look at it, you do end up with 2 pi. Okay, this is a length. It's a linear distance, so I'm going to use a linear unit. That would be 2 pi centimeters. Find the area of the shaded sector here. Okay, so we need this. We need the shaded central angle. So if I know this is 120, then the shaded central angle should be 360 minus the 120, or in other words, 240. So the 240 is what you want to use. 240 out of 360, and we're doing an area. So we're going to do a fraction of the area. Well, we know area is pi r squared. Okay, so this one's a little bit easier, but to reduce, you obviously can divide by tens. You get 24 out of 36. That, if you recognize it as 2/3, awesome. If not, you're going to divide out 12s, and you will end up with 2 over 3. And then we're going to simplify that as 64 pi. Okay, so then, let me put some equal signs there. So then we are going to either think about what is 2/3 of 64. It's 48, if you knew that. If not, you're going to rewrite this like that, and you multiply the tops. So you get 128 pi, multiply the bottom, and you get 3. Now, unfortunately, 3 does not divide into 128 evenly, so we are just going to leave the answer in this weird form, this improper fraction. Okay, if it reduced, we would reduce it. But units, we have a linear unit of inches. This is an area, so inches squared. Perfectly fine to leave an answer like that. Okay, 3 and 4 are more difficult. So if you pause and try those, and then come back. Okay, welcome back. So here's the area of a sector is given to you. So now we're thinking we got to work backwards to find the radius. Okay, it's always good to have a picture drawn if you don't have one. So I'm going to draw myself a picture. The measure of the central angle here, so this is O, is 315 degrees. So this whole angle here is 315. Okay, the sector AOB is 7 pi over 2. So A, we have B, and we're looking at this area. Okay, well, let's set up what we know. We know it's going to be 315 out of 360, and that's going to be times the area. So area we know is pi r squared. Okay, and when we calculate this, it's going to be equal to what's given to us as 7 pi over 2. Okay, so let's try to work through this. So first of all, I'm going to reduce this fraction. Okay, and I don't want to spend too much time on it, but you will get 7/8 when you reduce that. Pi r squared, and that's equal to 7 pi over 2. All right, so now we got to start getting rid of the 7/8 on this side to get r by itself. Well, you can multiply by the reciprocal. Your algebra teacher probably taught you this, but we're going to multiply both sides by 8 over 7. What that does is cancel all of these. So now I'm left with just pi r squared. And then over here, you can reduce some things. So the 7s are going to cancel, and then 2 divides into 8. So that's going to be 4, and then pi. Okay, now this is why we leave things in terms of pi, because now I can divide both sides by pi. So I end up with just r squared is equal to 4, and then you have r equals, again, officially it's plus or minus 2, but for geometry, we only care about the positive, or the positive length. We don't have a unit, so it'd be 2 units. Okay, last one. Here, we have a shaded region. This entire area is shaded. We're just missing the white segment. Now, it's always easier to add pieces rather than subtract them. So here, what I'm seeing is I have this piece and I have this piece. And those two pieces will make that shaded region. Okay, if you try to subtract off the white part, that is going to be more difficult. Always try to add pieces rather than subtract them if you can. Okay, here, we can figure out this angle measure, or we can just sort of visually see that that is 3/4 of the circle. And then with that 90 degrees, this is going to be a base of 8 and a height of 8 for the triangle. And then you're going to go along and calculate that. So 64. So in this case, you have 64 pi over 1. Well, 4 will divide into 64, and that'll become 16. This is just some tricks that'll help you. And then 1/2 times 64. So now I have 3 times 16, which is 48 pi. And 1/2 64, which is 32. And you do leave your answer in that weird form. These cannot be combined. They are not like terms. It's kind of like saying 48x plus 32. You don't combine those. So you don't combine 48 pi plus 32. So this would be your final answer. All right, good job today. We'll see you next time.